Hello, my name is Michael Laielli. I'll be presenting work done by myself, James Smith, and Giscard Biamby, all in equal contribution. We're advised by Trevor, Darrell, and Bjoern Hartmann. All of us are from UC Berkeley, and as a group, we have a combination of computer vision and HCI backgrounds. Computer vision is increasingly being used in sensing systems to detect objects and images. Object detection algorithms rely on massive amounts of training images which need to be labeled spatially with boxes and semantically with categories for all objects that you want your system to learn across many images. However, this presents a problem when you want to give a vision system understanding of your specific things. Deployments of such a system won't have examples of your favorite mug that you picked up while on vacation in Canada, for example. More generally, useful deployments of vision systems in homes might need to detect specific instances of things, and users might need to provide examples of them. So let's look at some solutions as to how a user might perform a labeling task today. There are really two leading paradigms. First, we have post-hoc labeling. In post-hoc, users collect images of their things with a standard camera, and then use separate labeling software to manually draw boxes around each object in an image. This is time-consuming, but provides high-quality pixel-perfect data. Here we've shown someone using Berkeley Deep Drive's scalable tool, sped up 10 times. On the faster end of the spectrum, we have a camera that has been slightly modified with an overlaid box on the display. The user moves the camera to fit the box to the object. This is much faster, but compromises accuracy due to the one-size-fits-all nature of the interaction. Another limitation is the user can only collect one object per image. So we have two labeling interfaces at opposite ends of a spectrum that we define here. On the x-axis, we have time spent collecting images and labels. Faster is better, so we'd like to see interfaces on the left side of the plot. On the y-axis, we have the object detection performance of a given model trained with data from a given interface. Higher is better, so we'd like to see interfaces near the top. What we've found is that they cluster in the following ways. Post-hoc is accurate but slow. It takes a long time to draw boxes around every object in every image. Overlaid is fast, but performance suffers due to the constraint of only one fixed size box per image. We wondered what could exist in the space in between. A tool in this space could provide a useful trade-off between speed and detection performance. In our brainstorming, we had an idea that leverages augmented reality to enable such an interface. AR capabilities allow us to anchor 3D volumes within a user's local environment. We thought that if we could use AR volumes to bound and track real-world objects in 3 dimensions, then we could easily recover the 2D boxes for any image taken from any vantage point. We created an interface for users to define the size, shape, and location of AR volumes in 3D. We called it LabelAR. LabelAR is an augmented reality phone application that helps you collect computer vision training data. The interface works in 2 stages. First, we have the users provide 3D volumes over real-world objects using standard translate, rotate, and scale interactions common in 3D applications. Users need only do this 3D labeling once per object. Notice that the user is labeling the objects before images are actually captured, which is inverted from the post-hoc interface. The bounding volume vertices are automatically projected from 3D into the 2D image plane using the AR tracking data. Then a 2D bounding box is easily recovered for each object in each image. The second part of the interface guides users to collect images from different viewpoints. Based on the arrangement of objects, we provide markers to indicate where the user should move the camera to in order to collect views from equally spaced rotation angles that break the image plane. Images are automatically captured as the markers are hit and turned from red to green. This allows the user to focus solely on the positioning of the camera and not have to worry about when exactly to capture images. Next, I'd like to talk about a few benefits and design considerations made with LabelAR. I mentioned out-of-plane rotations earlier. A common data augmentation strategy when training vision systems is to provide rotational variety by using in-plane rotations. These rotations, however, provide no new pixel data. Out-of-plane rotations can provide valuable new pixel data, which is a benefit that these in-situ approaches afford that the typical internet search and scrape technique does not. One particularly big time saver that we found was to utilize planar tracking provided by the AR API. This allows users to place objects at the right depth by just tilting the phone screen. It also saves time by automatically snapping bounding volumes to the right height. However, this does introduce a limitation that you can only collect objects that are sitting on planar surfaces. So right now, our interface suggests 24 static angles to guide the user to collect. We came to that number by conducting a short ablation experiment over a range of viewing angles. We found that the detector generally performs better with more viewpoints as expected, so we made a design decision to draw a line at 24 as a reasonable trade-off between model performance and the collection time and effort required by the user. So to summarize, we discussed 2 existing methods and introduced one new method, LabelAR. Now I'll discuss our user study and how we evaluated the performance of our interface compared to the other 2. To test our hypothesis that LabelAR will offer an approximately linear trade-off in terms of performance and time, we conduct a study to evaluate our interface as compared to the 2 baseline interfaces. First, we have users collect data with all 3 interfaces. Second, we train computer vision models on the collected data. And third, we evaluate the trained model's detection performance on holdout data that was unseen during training and observe the effects of the 3 interfaces. In the data collection phase, each individual study lasts 1 hour, where the user performs 3 main collection tasks, 1 for each interface. This includes a tutorial on how to use a given interface with some light guidance on how to follow computer vision best practices, such as it's good to capture more images and it's good to vary the viewing angle. The data collection phase also includes a time-limited phase where the user can decide to stop. Includes a time-limited collection phase where the user can decide to stop before the limit is reached if they feel they've collected enough data. For the posthoc interface, there is an additional labeling phase performed on a laptop since the posthoc image collection does not generate labels itself. We balance the user interface and object set combination so that in total across all users, each interface is used to collect each object set an equal amount of times. So let's check out the object sets in depth. So we carefully collected 3 sets for the study. Each set was chosen for variations in size, shape, and texture. Each set has 5 instances, which present a challenging fine-grained recognition task. For example, within the toy set, we have a front loader, excavator, backhoe, bulldozer, and dump truck. Notice that distinguishing between these objects is no trivial vision task, since they are similar in size, color, and low to mid-level textures and patterns. And this holds true for each of our object sets. After the user data collection is complete, we take their collected images and labels, and we train computer vision object detection models, particularly FasterRCNN model, resulting in 3 separate trained models, 1 for each interface. And we repeat this process for all 12 users. This results in 36 trained detection models, and those cluster into 12 models per interface. What we really want to know here is how well each model will perform in the wild, or in other words, how it would perform on new data that was unseen during training. So we feed it some new images that we call our test set, and these test images are of the same objects in the training images, but taken in completely new rooms and scenes. Each model gets tested on 120 new images. Some of the test images portray objects at different scales. Many of the test images have significant clutter throughout the scene, and some of the objects are partially occluded. We wanted to make this challenging so it would indicate how a given model might perform in buildings and various rooms it has never seen before. So our output here is a set of predictions in the form of 2D boxes and category labels. So let's zoom in on just one of those predictions. So here our model seems to correctly predict that there is a backhoe somewhere on the left side of the image. However, it seems a bit confused about the exact location. Probably the remote control threw it off. The question is whether this is an acceptable prediction. So to make that determination, we compare the predicted box to the true box in blue. We look at how much overlap there is between the two by computing the intersection over union, which is a self-descriptive ratio of 2 areas. The intersection of the 2 boxes over the union of the 2 boxes. An exact overlapping would yield a perfect score of 1.0, but in this case our model's location prediction was not that great and only managed a 0.27 IOU score. So it's standard practice to employ an IOU threshold of only accepting 0.5 or higher. So in this case, the prediction is considered a false positive. Let's look at the rest of our model's predictions on this image. And we see that it goes on to correctly predict 3 true positives. However, it missed the excavator on the right, and that results in a false negative. So over the 120 test images, we count up the true positives, false positives, false negatives, and use those to calculate precision and recall. Precision tells us out of all predictions made what fraction are good. Recall tells us out of all the things to be detected, how many were actually found by the detector. And then we combine these into a single score called average precision, which basically averages precision over a range of recall values. Now that we have a single detection score for each model, we can plot it against collection time. Here's a single detection model trained on data collected with the Posthoc interface. This model scored 0.48 average precision over 120 test images. It took a user roughly 9 minutes to collect the data that was used to train this model. Let's change that icon to a dot and plot the rest of the 35 models as dots. And let's denote the means with large dots. If we consider a roughly linear relationship between the overlaid and post-hoc interfaces, we could see the LabelAR mean is on the desirable side of this line. In other words, it's a bit more accurate and faster than we had hoped. So Posthoc has a mean average precision of 0.32, while LabelAR has 0.22. However, statistically, this ends up not constituting a significant difference due to large uncertainties in the y-axis. Let's view 95% confidence intervals. So there's a lot of there's large confidence intervals in the y-axis particularly, but what we can say here is that LabelAR has comparable detection performance to the Posthoc interface and is over twice as fast. So the Posthoc interface on average 16 minutes for collection and LabelAR 6.1. Compared to the overlaid interface, LabelAR is only 27% slower, but 11 times more accurate. So this is pretty good, higher and more to the left than we had hoped. So we're interested to disentangle a few factors that contribute to the encouraging result. So I'll discuss some performance factors, particularly label accuracy and data quantities. The first factor is labeling accuracy in terms of IOU. The average accuracy of the overlaid interface has a 0.45 IOU. Here we show what a user-produced label with a 0.45 IOU might look like with the true box in blue. We do the same for LabelAR and see an IOU accuracy of 0.5, which is significantly higher, but not by much. Posthoc had a much higher IOU of 0.9. This means a few things. Our study participants were top-notch at using the Posthoc labeling interface. 0.9 is about as good as you can do. To have achieved comparable detection performance, LabelAR must be compensating with other factors. Another factor to consider is how many images and labels were collected by the average user. On average, users took 37 images with the overlaid interface, which is also the number of labeled objects since the interface limits one label per object, one object per image. The average user took 29 images with Posthoc and labeled about 62.5 objects on average, which works out to about two objects per image. And users took exactly 24 images with LabelAR as enforced by the interface and labeled 118.5 objects on average, which is significantly more than other interfaces. So it turns out LabelAR users took more images that included all 5 objects, even though that in particular is not enforced by the interface. This ability to collect more labels in a limited amount of time could partially explain how LabelAR achieves comparable detection performance despite less bounding box accuracy. So for next steps, there's some things we can do to address the large confidence intervals in the y-axis and perhaps improve in terms of time and accuracy. And one way is to incorporate detectors in the app to assist the user with semi-automatic labeling in 3 dimensions. Another is to perform 3D reconstruction on the multi-view images and further enhance the label quality. A third direction is to employ active machine learning to have the interface propose next best viewpoint for the user to collect. In the grander scheme of things, we created LabelAR as a first step towards a platform for more interactive computer vision research. We plan to continue by adding interactive machine learning algorithms that continually learn and update based on user interactions. So in summary, LabelAR is an interface for fast collection of computer vision training data. It provides a useful trade-off in terms of collection time and detection performance, achieving comparable performance to the Posthoc interface in less than half the time. Compared to the overlaid interface, it was 11 times better detection performance, yet only 27% slower. And that concludes our talk, and I'll be happy to answer any questions. Thank you.
We have time for a couple questions. One in the back.
I'm Hongguo from Carnegie Mellon. So I have a comment and a question. So comment is, maybe it could be interesting to put the objects on a surface that you can kind of show different images to kind of increase the diversity of the background. And the question is, so you show that, for example, when you deploy the model kind of in the real world, you see there's a drop in accuracy because you have not seen in those cases. So I'm wondering whether it's feasible to use this approach in those wild environments and automatically collect the negative examples while seeing the other distractors, like the control.
Yeah, so great comments. I think in the first one, I think anything you can do to increase the diversity of the background would be a good thing. If we could implement the semi-automatic detection and perhaps tracking, another thing is you could pick the object up and kind of move it around. But